Hello, in this video we're going to take a look at calculating the center of mass of a region in space, particularly when you have a non-uniform density in the region. Now I find it nearly impossible to talk about center of mass of an object without also talking about average value, because as we saw back in previous video with double integrals, we can find the center mass of a region in the plane by essentially finding the average value of x and the average value of y. Now we did that under the assumption that there was uniform density. Um, in this one I definitely want to consider non-uniform density. But here we go. I need to talk about average value first, because the average value of a function is defined as the integral of the function divided by the integral of 1. Now back in Calc 2, this was just a single integral, where you would integrate the function, which would essentially give you the area underneath the curve over whatever interval you were doing. And then when you integrated 1, it just gave you the length of the integral. Sorry, it just gave you the length of the interval. So that area divided by the length was essentially saying how tall would a rectangle need to be to have the same area as underneath the function. So it was giving you the average height. Right? Integrate the function, divide by the integral of 1, essentially divide by the length of the interval. When we moved to double integrals, we said take the double integral of the function over the region and then divide by the area of the region. Well, the area of the region is just the double integral of 1. Right? Now we're looking in space, and I would say that the average value of a function is the triple integral of the function over whatever three-dimensional region you have, divided by the integral of 1 over that three-dimensional region. And that triple integral of 1 is the volume of that region. So finding the average value is integrating the function and then dividing by the length, the area, the volume of the thing that you're integrating over, depending on how many dimensions you happen to be in. Now, if the density is not constant, the center of mass is not simply taking the average x value and the average y value and the average z value. It's a weighted average. Now, what do I mean by a weighted average? Take a look at this example here. Okay. So this is just a simple example with numbers. We're not doing integrals yet. If I give you this list of numbers, 1, 2, 5, 3, 7, 3, 9, 2, 5, 3, 7, 1, 4, and said find the average value, you'd say, oh, well, average, you just add them up and divide by however many there are. So 1 plus 2 plus 5 plus 3 plus 7 plus 3, you can write that whole thing out and then divide by, there's 13 of them there. But I want to write this a little bit differently in that I want to say, hey, I've got the number 1 in there twice, right? There's a number 1 right here, and there's a number 1 right there. So I'm going to write that as 1 times 2 because I have 2 of them. Likewise, the number 2, I think, is there twice. So there's 2 times 2. And the number 3 is there 1, 2, 3 times. So I'm adding 3 times. I can write that as 3 times 3. The number 4 is only there once. The number 5 is there twice. The number 7 is there twice. And the number 9 is only in there once. So equivalent to adding them all up, I could write it this way, in that I'm listing each of the numbers that appears only once here, 1, 2, 3, 4, 5, 7, and 9, and multiplying each by the number of times that they appear. I'm essentially giving each one a weight. That is, the 3 is weighted 3 times because it appears 3 times in the list. The 9 is only weighted once because it's only once in the list. Right? And the number I'm dividing by is the total weight of all of them. The weight of the number 1 here is 2, the weight of the 2 is 2, the weight of the 3 is 3, 1 for the 4, 2 for the 5, 7, 2 for the 7, and 1 for the 9. If I add up all those weights, 2 plus 2 is 4, plus 3 is 7, plus 1 is 8, 9, 10, 11, 12, 13. The total weight there is 13, and I'm dividing by 13. So I think of this as a weighted average. If I just took the average of the numbers 1, 2, 3, 4, 5, 7, and 9, it's a little more than 4. It's like 4.4 something, right? But this average, because some of these lower numbers appear more often than the higher numbers, the average is a little bit less than just the strict average of the numbers taken only once each, and the average here is 4. Okay. So I'm thinking of this as a weighted average. Now, when I go to find the center of mass of a region in space, and that region has non-uniform density, then what I'm going to do is I'm going to take the region. I mean, this is an integral, right? You're going to take the region, cut up on a bunch of little small pieces. For each piece, you're going to figure out how much is there and add them all up, right? So I'm going to do a weighted average of the x's to find the average x value. I'm going to do a weighted average of the y's to find the the average y value, and the weighted values of the z to find that z component of the center of mass. So if you look at that thing, let's look at the x component of the center of mass. Whatever region you have, you cut up into a bunch of little rectangles. These little rectangles have volume dv. If you multiply that volume by the density function, then you get a little bit of mass. And now I'm multiplying it by x because I want to find the average x value. So I'm looking at this integral right here in the numerator. Each little cube has an x value, and I'm saying how much is that x value worth? Well, that it's worth as much as the mass that's in there, right? So whatever that x value is, it's being multiplied by its weight or its mass, just like these numbers were multiplied by their weight. Places where it's more dense, you will have more mass in that same little rectangle, and that x value will count for more. Places where it's less dense, you have less value, and it counts for less, right? Less mass accounts for less. And then after you do that, this is what would be called the moment. I mean, the book would call this MYZ. This is the moment away from the YZ plane. I mean, to measure from the YZ plane, you're measuring x values. It just always seems funny to me to say that x bar is MYZ over M. It's like, how about if we just say it's the average, it's the weighted average x value divided by the total mass. And the average y is the average weighted y value divided by the total mass, right? So the MXZ and the MYZ, I think they complicate things here when you're just saying the average x. It's a weighted average because the density is not the same. Take the x's, multiply by the density, integrate over the region, divide by just the density over the region, the integral of the density, which is the total mass. Okay. I want to do one example of this. It is the same example I calculated the mass of in the previous video. So this is a cube. All the edge lengths are 1, but rather than sitting it down at the origin, I have one corner at the point 1, 1, 1, and the opposite corner at the point 2, 2, 2. So all the x and y values are between 1 and 2. And I'm giving it the same density function I did before with 1 over x, y, z. So the place that's the most dense is the point 1, 1, 1. It has density 1 there. Notice at the far away corner, 2, 2, 2, the density would be 1 over 8. And so it's less dense that further away. It's not entirely that the closer you are, the more dense it is, because the level surfaces of this function are these curved sort of hyperboloid things that they're all nested, so that essentially the closer you are to the origin, the bigger value you're getting. Right? But anyway, if the density function was constant on this is a cube, I would expect the center of the mass to be right smack dab in the middle, with x bar, y bar, and z bar equaling 1.5, right, halfway between 1 and 2. But with this density function favoring the closer stuff to 1, 1, 1, as in heavier in 1, 1, 1, then I would expect not to have 1.5, 1.5, 1.5. That's my center of mass. So here's the calculation for x bar. I'm finding the weighted average x value. So each x value is being multiplied by this density function and then integrated dv. I'm choosing to do dz dy dx. It doesn't really matter here. It's a rectangular region, right, or a cubical region. The x's cancel out. The denominator is the mass that we calculated in the previous video, which we saw was log 2 cubed. Let's see. So once those x's cancel out there, you get the integral of 1 over y z, and yes, it's a rectangular region. I can write this as a product of a function just of x just of y and just of z, and I can do those integrals separately and then multiply the results together. This first one has an integral value of 1. This one is log 2, and this one is log 2. We end up with 1 over log 2 as being the x value of the center of mass, which is about 1.44 something, so a little bit less than 1.5, which is what we expected to happen. I think because of the symmetry of this thing, you can see that y bar and z bar would also be the same. Just a quick check here, if I plugged a y in here instead of an x, then the y's would have canceled out, and this would have been an integral of 1 over x, but that would have been an integral of 1, and you'd still end up with a log 2 times 1 times log 2, and some of the log 2's would cancel out, leaving just a 1 over log 2. So the symmetry of it allows me to say that the center of mass is there, with x, y, and z components being 1 over the natural log of 2. So there you go. The center of mass of an object is the weighted average for the x value, for the y value, for the z value. You're finding the average value, but with the density function, you're finding the weighted average.